All right, hello everyone. This is Dr. Adel ElSafty, and I welcome you to the course of Prestressed Concrete. It's cross-listed for both undergraduate and graduate students. It's 8-week session, and I assure you that you will love that course. It's an extension of what you studied earlier about reinforced concrete, but this is much more interesting product, much more interesting material that you're going to be working on as far as design, as far as analysis. So I assure you will love it, and I'm going to be posting PowerPoint presentations and narrated ones and videos online so that you can enjoy that course. Basically, this is CES 4711 for undergrad and CES 6715 for graduate students. Again, you can reach me through my email, as you can see here on the screen, or my phone, or if you'd like to have my cell phone as well, I can give that to you. Or you can stop by my office in Building 4 at UNF, room 1212. Basically, to give you an introduction, an idea about the prestressed concrete, there are so many applications for that. It's not just bridges, as you can see here in this slide, the Sunshine Skyway Bridge, and that is using prestressed concrete elements, but it's not just for bridges. It can be for commercial buildings, it can be for residential buildings, it can be for churches, and it can be for parking garages as well. So many applications that you can use. So here, for instance, some prestressed concrete elements in the Skyway Bridge, and others which is in prestressed concrete components, as you can see here in this bridge to the left-hand side at the bottom corner, and to the right bottom corner right here, you can see segments of prestressed concrete components for accelerated bridge constructions. And in that precast parking garage, you can see the exterior facade or the exterior part of it. I wouldn't say it's a facade, it's more of a column. It's a structural component that is carrying some loads, and it's 42 foot long, and it has 6 feet as far as the width, 2 feet as far as the depth, and the height is 42 feet, and it's being cast as one piece. So there is no splice or anything like that, it's just one piece. And as you can see in that slide, there are several prestressed concrete components, and some of them are the column that are supporting the girders and the girder that is supporting the slab. But in that case, we're not going to say it's a slab, it's something called a double T. And you probably noticed in the syllabus that I posted recently that you will be designing one of these double T. So if you go to the parking garage at UNF or any other place, you will see double T primarily is the major prestressed concrete component that you'll have, and can have 60 foot long, it can have 50, it can even go 100, 125 as far as feet as far as the length. Prestressed concrete for double T's, for any other beam, for columns, for the stairs, and for any shear wall connections as well. So I just wanted to show you the great accomplishments that the designers have done as far as prestressed concrete. So for that building, for instance, the roof is prestressed concrete and is supported on girders, and the girders are prestressed concrete supporting columns that they're also prestressed concrete. So the whole entire structure has prestressed concrete in that single story beam column construction. Also in the multi-story beam column construction, as you can see here, you have prestressed concrete, especially in parking garages. In addition to that, another task is that you will be required to design a beam. It is not similar to the reinforced concrete beam in the ultimate design that you have a reinforced concrete design class. It's going to be much more interesting. The reason I'm saying it's interesting, you have something called ASH2 type girders or Florida I-beam girders. You will be designing both by hand calculations and using a software, as I listed on the syllabus, under Leap software, Conspan software, under Bentley. The ASH2 type girders is not just one type. There are several types, ASH2 ASH2, ASH2, and so on. And you will be designing that. So why I'm saying this is different than the reinforced concrete, and I'm going to exactly explain the difference between reinforced concrete versus prestressed concrete. We're going to be discussing that how can you have bigger lengths for prestressed concrete. So for reinforced concrete, for a bridge, for instance, you cannot exceed like 50 feet or so. In prestressed concrete, you can get to 120, 130 feet and more. And it's going to have shallower cross-section as well for a reason. And the reason is that you are applying a compression force for the concrete so that you can mitigate this cracking tendency of concrete girders. As you know, if you have a plain concrete and you apply the load, the moment capacity for it is nothing but a very small moment capacity, because the concrete is going to reach the cracking, and the cracking, which is F sub R, which is 7.5 square root of F prime C, or the modulus of rupture, can be reached very quickly. So if you have 4,000 psi concrete, you can have around 477 psi as far as the modulus of rupture, or the tensile capacity of the concrete. So that will give you a moment capacity that's very small. Then move to another level and put steel reinforcement at the tension side that will increase the moment capacity. So you're going to have a nominal and ultimate moment capacity that is way bigger than what you had for plain concrete, for a reason. Because the concrete, as we know, is strong in carrying compression, which is going to be at the top of the beam. But when it comes to the tension, it is not behaving very well. It can only take 477 for 4,000 psi concrete, meaning that you need another material so that it will capture this load, it will capture this kind of stresses, it will arrest the cracking, it's going to close this cracking, and this is nothing but the steel, the reinforcing steel that you have. We've known that in reinforcing concrete. Now we go to another level, which is a totally new level, wonderful, which is apply pre-stressing force by having these cables that are 4 times to 5 times stronger than the reinforced steel, and then apply tension force to it, and then release this force. So the concrete itself is going to be under compression. And the beauty of having the concrete under compression is because the concrete itself is able to carry this kind of compression. So we're going to go through this and see how much gain did we get. And what is the advantage? Did we fully utilize the materials, both concrete and steel, or not? Were we able to go longer spans or not? Were we able to find shallower or to get a shallower cross-section for the same span or not? Were we able to avoid having cracking so that you will have a concrete that is intact and that will sustain any kind of adverse environmental attack or not? So we're going to talk about it. So you will see this kind of astrotype girders, and at the bottom of that girder, you will see these dots, which is nothing but the location of the strands. We are going to interchangeably talking about tendons and strands, pre-stressing tendons, pre-stressing strands, and I'm going to explain to you what the differences are later on. So all of those are under tension, and they can have a straight pattern, or they can have draped or harped strands. We're going to be discussing that and see how we can calculate it. And by the way, the picture that you're seeing here is the output of the LEAP software, the conspan. In reality, the astrotype girders, or the FIB rather, looks like that. It's a pre-stressed concrete girder that can span 100 over 120 feet long, and as you can see here, it will be working perfectly well, and you can have these pre-stressing strands at the very bottom in the tension side, so it will sustain that kind of huge moment that you're having. And you will notice that all this pre-stressed concrete element will have certain camber. So this camber is because of the pre-stressing effect that will apply certain camber, and that camber will be reduced, and the beam will be level later on when you have the dead load and the live load applied on the beam. So this lecture is just like, I want you to kick back and relax. This is very casual. This is just to give you an introduction about what we're going to be seeing and how much suffering you're going to have with me for 8 weeks. I assure you that I'm going to make you sweat, and you're going to make you getting tortured doing hand calculations and software, and you are going to be perfect designers for pre-stressed concrete by the end of these semesters. Other applications, as you can see here, everything in this parking garage is made of pre-stressed concrete. So the precast concrete columns with this support that's supporting the girders, the girders supporting the double T as well. And there are several types of double T. And you will see in the other presentation that I'm going to show you that there is a free kind of handbook that I have for pre-stressed concrete For whoever is interested, I can give it to them. I only have 10 copies left or 8 copies left. This is what you're going to be seeing in your design. That's another type of pre-stressed concrete. Another product which is fantastic, as you can see here, is the whole core slab. So the whole core slab can be used in hotels, it can be used in buildings, residential, commercial buildings, and is a fabulous product that has a wonderful application in all of our construction industry. And the main element that I want you to be familiar with is solid flat slab, and that can be pre-stressed, and the one next to it, which is a hollow core slab, and then the third one, which is a double T, and then the single T, and then from that you can design the ash to girder or the FIB. So this is what we were going to have through our pre-stressed concrete class. And what the idea is primarily if you have a stack of books and you'd like to hold them together. Imagine that you have 10 or 12 books and you'd like to hold them together. So basically, if you lift them up, they're going to be just like falling apart. So in order for you to have them in place, you have to squeeze them in. So you have to apply pre-stressing force, or to have to apply this compression force in order for you to mitigate this kind of failure. So imagine this is a bridge girder. And if you'd like to double the number of books, meaning that you have 20 books and you'd like to hold them with both hands, in that case, your only option is to apply huge, bigger amount of force in order for you to squeeze this in, and that will withstand its own weight and any other force on top of it. That's basically what the pre-stressed concrete principle is. To the right-hand side of that slide, you can see here, if you have a concrete beam that is going to sustain loading of a truck, a very heavy loaded truck, it's going to bend, it's going to use that crack at the bottom, which is the tension side, and you will need to put this steel reinforcement in order for you to stop the cracking and hold this concrete beam together. Pre-stressed concrete application, as I mentioned earlier, is adding another layer of protection, which is applying stretching force of tension to the tendons, at the same time compressing this kind of beam so that it will withstand the same loading with no much sagging and no much deflection. And we are going to go through the process, and I'm going to explain to you later on the differences in pre-stressed concrete, which is something called post-tensioning versus pre-tensioning. It's primarily about when do you pour the concrete, meaning you stretch the cable first. And in the form, you pour the concrete. And once the concrete hardens, you cut the ends of this pre-stressing strands so that it will compress the beam and it will be pre-stressed. That is pre-tensioning. The other one, which is casting the concrete with a tube, a hole inside it, and then insert the pre-stressing strands inside the hardened concrete and lock it at one position, and with a jack stretch it from the other side. When you stretch it, you apply compression force to the side of the beam. That is post-tensioning. Some of them are for precast applications, the other are more suitable for on-site, like segmental bridges and other applications as well. So we were going to be discussing them. For our class, you will see the class and the catalog description that we're covering pre-stressed concrete behavior and design, and we're going to be talking about pre-stressed and post-tension girders. So we're going to cover some basic elements, and I might add some continuous beams as well if time allows. There is no required textbook for this, but there are 3 listed ones. There is one which is $13, which is the first option. Here is at the bookstore. You can either have it electronically, and I listed that in the syllabus if you wish. And the other one, which is by Edward Nawi, and the third one by Antoine Naumann. So any of these books or any other book or any resource online will be helpful. Or if you'd like to rely on my magnificent presentations, feel free to. You don't have to buy the book as the course objectives are to analyze and detail the pre-stressed concrete, perform flexure design, identify loading requirements, and design statically determined pre-stressed concrete beams, check the capacity of the beams, calculate the camber and deflection, calculate the losses and stresses in the composite system. If you feel that I'm going so fast, don't worry about it, because 2 things. It's going to be posted online, right? So you're going to watch it and rewind it and just make it slower if you wish. In addition to that, there is another presentation which is pretty much identical to that with more details. So don't worry about it. I'm just trying to cover as much stuff as possible without boring you to death because the semester didn't even start. So I'm trying to overwhelm you with some work today before you start tomorrow. The course objective is an 8-week session, so everything is going to be online. So in addition to the requirement that we have that you're going to be doing some presentations, at the end you're going to have a video that you're going to submit to me. I will try to develop some quizzes online so that we interact and they see what the weak points are. And you're going to enjoy that class. So the breakdown, tentatively, that's what you see here on the syllabus. It might be different for undergrad versus grad students. So you have percentages for the serviceability, crack, and shear presentation, which is the first one. The second one, which is ASH2 and FIB, crack control, whole course lab, and double T, and then the final videos. So if you have any questions, feel free to email me. These are the list of the topics that we're going to be presenting. And these are the requirements at the very bottom with the red color. And these are for, I believe, the graduate students. The undergrad are going to have something less than that. So we're going to be discussing that. And you can access your syllabus. If time allows, then we're going to have a pile design, which is pre-stressed concrete pile, which is fantastic, 18 by 18 or 24 inch by 24 inch pre-stressed concrete piles. And we built one of those in Panama City, Lynn Haven area here in the Panhandle with pre-stressed concrete piles using not pre-stressing steel strands, but rather carbon fiber that we got from Japan. And the stirrups were glass fiber, and we've done that last year, and I'll be glad to share with you the findings and the design of that. It's a very interesting project for a reason. Of course, you know why we're using carbon and glass instead of steel. Do you guys know why? If you have bird structure, bird concrete in the soil, and something happens to it, like corrosion and all this kind of sulfate attack, corrosion primarily is the one that's attacking the steel reinforcement. If you have glass or carbon, it's a non-corrosive material, so you don't have to repair, because there is no repair for that. It's going to be just primarily replacement of the piles. Course outcomes listed on your syllabus. So I'm just gonna stop right there and for the first lecture, and I'm gonna provide you with a more detailed one later on. And as I send you in the syllabus, one that I had, it was recorded earlier, so you will see in it some stuff that's saying that you're gonna come to class to present. This isn't gonna be valid this semester. Everything is gonna be online. So I hope that you guys are going to enjoy the class, and I'm sure you will. If you have any questions, feel free to email me, and we will have a wonderful time together this semester. Thank you so much, and have a great day.